Okay, amazing. A few people might join, but I'm going to start now. So welcome everyone to this crossover event for our IAQM and land condition early career networks. This event has been put together in collaboration with the Society of Brownfield Risk Assessment, so a big thank you to them. This is actually the first crossover event we have held for our two early career networks, and we are really keen to explore opportunities for interdisciplinary learning. So I hope it will be really useful to explore a topic relevant to both land condition and air quality professionals, and also to give you the chance to hear from different perspectives. Before we kick off, I'll just do a bit of housekeeping. So this event is set up as a meeting rather than a webinar, so it can be a bit more informal and discursive. However, we are, of course, we've got three excellent speakers with us today. I'm delighted to be joined by them. So when they are presenting, please do mute yourself and turn off your camera to limit distractions. And then please do turn these back on during the Q&A session after each presentation so that we can have a bit of a discussion. For that Q&A session, you can either type questions into the chat box, which will be read out on your behalf, or if you raise your hand using the reactions button on your Zoom, then we can come to you so that you can ask questions in person. Just to let you know that these presentations are being recorded and will be made available on YouTube and our website afterwards. So I'm now delighted to hand over to Emily Portergill to introduce our speakers. Emily is a member of the IAQM Early Careers Working Group, and they have been instrumental in organising this event, so a massive thank you to them. Emily, over to you.
Hello, hi everyone. So we have three speakers this afternoon. So firstly, we have Melanie Lipsham. She's giving a talk on sick building syndrome, and Melanie is an environmental engineer at Leap Environmental after graduating with a degree in Earth Sciences from Cardiff University. Then we have John Andrews giving a talk on the uncertainty and vapor intrusion risk assessment. John is an associate in the Environmental Protection Group, specialising in vapor intrusion and ground gas risk assessment. And John has over 20 years experience in contaminated land consultancy and 9 years in organic chemistry research. And then finally, we have Laurence Caird, who's an associate director at Air Quality Consultants giving a talk about Avenue Coking Works, which is a case study in land remediation and air quality monitoring. Laurence has 15 years experience in air quality consulting, working on a wide range of assessments, including road traffic, airports, and heating and energy plants. So yeah, we'll have each speaker will give a talk, and there'll be time to ask questions after. So yeah, as Ethne said, if you have any questions, please write them in the chat box or feel free to raise your hand. Hope you enjoy.
Cool, I'll just share my presentation. You can see that okay, hopefully.
Yeah, we can see that okay, but you're a bit quiet, Melanie. You can move a bit closer. Yeah, thank you.
Sorry about that.
Yeah, it's a bit better. Thank you.
Okay, I'll speak up anyway. Okay, so I'm Mel from Leap Environmental. I'll be starting off the talk today on indoor air quality, and this is a case study on how vapor intrusion led to a possible case of sick building syndrome. So I worked alongside EPG. John Andrews from EPG is giving the next talk today as well. And so I'll be going through Leap's involvement and also touching on the work that EPG did on this as well. And it's covering a recent case study of vapor intrusion within a residential property. So quick bit of background. So we were contacted in February of 2020 by a property developer following a recent complaint of a gas odour by a resident. The odour was primarily in her open plan kitchen living room area on the ground floor, and it was described as an earthy or eggy kind of odour. The property had been constructed 1 year previously, so it was quite a new build property. And the resident had started to feel unwell, lethargic, drowsy, itchy eyes, and was temporarily moved out of her house. So just before these symptoms occurred, her Antico flooring had been lifted across the ground floor. The adhesive attaching this flooring had been buffed off, and then the floor had been latexed. So the initial challenge was corresponding with a resident who was very, very anxious to solve this problem. And there was quite a bit of time pressure as well, because she'd obviously been moved out of her home. And we were the consultants previously involved in this site. So from desk study through to the intrusive investigation, all the way through to verification when the properties were built. So our first action was to look at the background of this site, do a reappraisal of all the historic desk study information, investigation data, and check our conceptual site model for this site. No gas risk had ever previously been highlighted here, and it was historically a landscaped garden and woodland area associated with a property to the north. So at this stage, nothing obvious to identify why she might be having these symptoms. So following the background research, we quickly mobilised the site and carried out some ambient monitoring for bulk gases and VOCs in the ground floor rooms, as well as where there were incoming services and penetrations through the slab, so under her kitchen sink, and through the subfloor space via the air bricks. And as part of a previous service inspection on the property, when they were trying to rule out a gas leak, there had been a hole drilled in her kitchen floor as well, so we monitored through that too. And the monitoring recorded low concentrations of bulk gases, up to about 0.1% methane and carbon dioxide, so nothing significant there. And generally, VOCs were recorded up to about 0.5 parts per million. And this is with the exception of that hole in the kitchen floor, where we recorded 13 parts per million. So this wasn't necessarily significantly high, but it was the only location of anything to note. So the next stage of the investigation was to go and collect some vapor samples. So we did this using SoBRA canisters. We also installed a vapor pin in her kitchen floor. So this was given that the odour had started once the floor had been lifted, and this is where we'd found 13 ppm. This kind of led us down the route towards looking at her flooring. And we also collected control samples from an adjacent property, and also ambient air outside the property as well. And this was a mix of kind of snapshot, collecting a sample over 5 minutes, as well as slow release canisters over 2 to 24-hour periods. So to see if there was any variability of when the vapours were occurring. And samples were tested for VOCs and TICs, those are tentatively identified compounds, with concentrations generally inconclusive. We did record pentane and isopentane in the air and some subfloor samples, but nothing at that stage to indicate a source of her health problems. So our next step was to actually core through the ground floor slab and look at the soils underlying the property, to kind of see if it was a potential source, or at least to rule it out at that point. So we cored through the ground floor and conducted hand augers beneath the property, with testing completed both on the soils beneath the site and the ground floor slab, and like the makeup of the ground floor. We also did headspace testing with the PID on the soils beneath the house. So from the core, the floor material was made up of a thin layer of screed, 90 millimeters of concrete, and up to 380 millimeters of polystyrene insulation. So we separated out each of these layers, testing them for the VOCs and TICs, And whilst the concrete and the screed did not record any measurable concentrations of VOCs, we did record a tentatively identified compound called 2-ethyl hexanol, and that was both in the concrete and the screed layer. Testing on the soils and the headspace testing ruled out the soils as a source with nothing significant recorded there. So we knew it wasn't coming from something underlying the property at that point. And it was at this stage that we got into contact with EPG and with John Andrews, and they carried out research into this project. They undertook research into the construction products used in the house, and looking into any potential VOC release, and reviewed all data that we had collected to date. So compounds pentane and isopentane and 2-ethyl hexanol had been identified in elevated concentrations within the screed and concrete floor in the kitchen, and isopentane had also been recorded in indoor air samples. EPG carried out research into these compounds. They had quite extensive amount of information that they went through, and it looked as though 2-ethyl hexanol, called 2EH for short, it was looked like the most likely source from their research. So 2-ethyl hexanol could be released from vinyl flooring under certain very specific conditions. So alkaline hydrolysis of adhesives which contained phthalate plasticizers by alkali oxides, which can be found within concrete. So this indicated possibly that the flooring had been placed when the concrete was not sufficiently dry, which created conditions that could release 2-ethyl hexanol. And further research by EPG found that this compound 2EH had previously been a cause of a condition called sick building syndrome. And symptoms of this sick building syndrome included irritation of the eyes and the upper airways, headaches, coughs, and fatigue, which was very similar to what the resident was experiencing in her home. So at this stage, EPG considered that this compound was the probable source of the odour and health complaint, although further sampling was required to actually prove this. At this stage of the investigation, we'd not been able to identify 2-ethyl hexanol in measurable concentrations in the indoor air sampling completed. From their research, EPG found a concentration of 0.4 micrograms per meters cubed was the target level for this compound, above which health effects had actually been recorded in previous studies. So the challenge at this stage was to find a lab that could not only detect 2-ethyl hexanol, but also at a low enough detection limit in air samples to be able to compare against this 0.4 micrograms per meters cubed. So we got in touch with the lab Element, and they actually brought in a standard for 2EH, and they completed a number of tests against this. And they confirmed that they could detect 2EH up to 0.138 micrograms per meters cubed, which was ideal for what we needed to do. And to be able to detect this compound, we had to use thermal desorption tube monitoring. So we went back to site and carried out this sampling method over 24 hours. So basically it's a tube containing an adsorbent material. The air is pumped through the tube for 24 hours. Tube's then sent off to the lab where it's heated and the analytes are desorbed or thermally extracted and analysed. And using this method, we collected 2 samples, one from the living room area and the kitchen area, and we recorded between 11.5 and 12.4 micrograms per meters cubed. So these were obviously significantly higher than the 0.4 screening value that we were going against. So following this, it looked very likely that this was the cause of the health complaint, and EPG came up with some remedial works that should be undertaken on the property. So this involved removing all of the original PVC flooring and the screed that had been placed on this concrete, and to make sure all service entries were sealed with a suitable sealant as well. The concrete was then heated to reduce the relative humidity to less than 75%. This was to prevent further reaction occurring, because it was likely that the damp concrete in the first place was the reason for the reaction to occur. The floor was then sealed with an epoxy resin, a low alkaline screed was placed, and the Antico flooring was reinstated with a dry bonded adhesive. And these measures were used to prevent any further reactions occurring, and actually to stop more 2-ethylhexanol being generated. In addition, the Antico flooring would also act as a seal to removing the pathway of the 2-ethylhexanol that could be still within the concrete. The property was then ventilated, and LEAP returned to do some verification monitoring. So the monitoring was undertaken. Initially, we still recorded elevated concentrations of 2-ethylhexanol. So these were thought to still be residual vapors from the recent remedial works. The property obviously wasn't being lived in at this stage, so natural ventilation, people opening doors and windows regularly wasn't occurring. So following further ventilation again, we did record 2-ethylhexanol below the lab detection limit in both samples from the kitchen and the living room. And this was by September 2020. So as a conclusion, to be able to have a quick and safe resolution on this, we needed an agility in arranging labs, mobilizing site, a flexibility and open-mindedness to where the investigation took us. We obviously went into this not really knowing what we were going to find or what we were even looking for, and also having the ability to know when we got to the point that we can't go any further and needing to call in DPG to assist with the investigation, and also having to work with quite a few different people: the client, regulator, the resident, the local authority, environmental health officer was involved throughout, and they were ultimately the people to sign off the plot. So yes, it was quite a task, especially during a pandemic. So yes, that's the end of my presentation. Any questions?
Mel, that was really great to hear from your presentation. Yeah, if anyone has any questions, please do put them in the chat box or raise your hand. That would be perfect. Just give it a minute. Sometimes people could take a little while to type them in. Okay, maybe you gave too much of a comprehensive presentation, Mel. Amazing. Did you have one, Honor? Just see that you've unmuted.
Yeah, I can ask a question if that's okay. So it's thank you for that. It's definitely something new to us from air quality work, because our surveys they definitely, well, not as labor. Well, obviously we're not drilling holes in someone's kitchen, and yeah, so let's say our surveys they are not as labor required, but I wanted to ask you, what was the biggest challenge with this whole survey, and how long it actually took you to from starting of your survey to actually figure out what is happening, and then to go through this whole remediation?
So yeah, it started the whole process went from February 2020 to September 2020. So that's when it was kind of concluded. So quite a long period of time. I think John might remember exactly when we got in contact with them. He might not, but yeah, I can't remember exactly what time we worked out the what the issue actually was, but it probably was around summer, I think June or July, that we figured out the cause, and then after that it was into the remediation works. So I think the biggest challenge probably was reassuring the resident whenever I had to go around and do the monitoring. She was very distressed. She came and visited every time I was there, and yeah, it was doing the investigation was it was kind of fairly not simple, but kind of standard what we do. But yeah, it's definitely reassuring the resident and helping calm her down.
And just one more follow-up from this one. So how this lady felt about moving back in? Did you monitor after as well when she was there? Like someone was in contact with her? Because if she was obviously quite distressed in this whole process, which you would be because it's your home, how did she feel about just basically being back?
Well, last time I spoke to her, she was extremely nervous, and I don't actually know, because we only went as far as signing off the plot, getting it through the local authority, and so I don't actually know if she moved back in or how she was when she moved back in. We only did the monitoring after the remediation works, not after she had been living there.
We've had another couple of questions come in as well. So the first one is, who was the regulator you referred to?
So the regulator was the environmental health officer of the local council. I can't go into too much detail exactly which council or where, but yeah, it was the environmental health officer was the regulator we were in contact with.
Thanks. And then the next one is, well, there's two questions in this one. So what were the initial gases you were investigating? And was there a specific reason why these were selected for investigation?
So initially we were just kind of doing a screen for anything anything that could be affecting her, that is air quality or vapors. So it was just the bulk gases from our GFM that we had and our PID monitor to see as an initial screen. And then from that, it led into what the labs could test for from our SoBRA samples. And yeah, just kind of trying to get a sweep of what, because we didn't know what we were looking for. So it was kind of testing for as much as possible almost.
Can I add a quick point in there, Mel, actually?
Yeah.
Because initially there were really high concentrations of pentane, isopentane identified in the subfloor. And concentrations, so they come up as aliphatic C4, C6 at high concentrations, and specifically identified tentatively as pentane, isopentane, which kind of indicates that you're getting high concentrations of these gases degassing from the polystyrene, which hadn't been allowed to cure or fully cure. So once expanded polystyrene is produced and cured, it's supposed to be stored for a period and allowed to degas, like a lot of products that go into properties, they degas. And this one looked as though it was degassing beneath the floor, and that was a really high concentration. And concentrations are often a bit unreliable in TICs, and in particular in this case, and we kind of discussed with the lab a lot, they were being quite highly exaggerated for some reason, one that I still don't quite understand. But it certainly pointed initially that you get these really high concentrations of pentane, isopentane, and we thought initially that it was a kind of a more standard vapor intrusion issue, albeit from the insulation beneath the floor slab. And it wasn't until we kind of looked at the concentrations in indoor air and thought, well, actually they are elevated, but they certainly wouldn't cause that problem. And whilst concentrations in indoor air are highly variable, it didn't quite add up. So it was only really when we looked at a TIC from the actual floor material itself, 2-ethylhexanol, which to me, even as a chemist, I thought, well, that doesn't sound too bad. And then you kind of look into it a little bit more and you go, okay, blimey, that actually, particularly in Scandinavia, is really highly recognized as being a source of sick building syndrome because of this issue of people putting flooring containing phthalates or using glues that contain phthalates onto concrete that hasn't cured to really high pH. And so it kind of required quite a change of idea and a change of approach, really, and hence the kind of Mel's comment at the end about being kind of flexible in how you view things. Don't we often go down a particular line of investigation, but you need to be kind of flexible enough to branch off and look into other areas that you may have kind of little experience of. And I think just a final point. So this is probably a much wider issue. It's a widespread issue in Scandinavia. If you do a search on UK literature, you don't find a single thing on 2EH and indoor air, let alone how it's produced. So it's probably quite a wider problem, particularly given that developers don't allow usually the full time for curing or drying of concrete floors before they move on. So it's potentially quite a widespread issue.
Thanks, John. That was a really good explanation there. Time to move on to your talk anyway. So go ahead.
Okay, I'll just share my screen here. Okay, so there's a slightly different talk. So this is a kind of a more theoretical talk. So it's not a case study. So what I want to go through is really to discuss uncertainty in vapor intrusion risk assessment. And I think most of us as contaminated land consultants or working in councils or whatever have some knowledge of vapor intrusion and vapor intrusion risk assessment. But I think there's probably not so many of us take vapor intrusion risk assessment to a more detailed arena where you really need to understand the uncertainties involved in order to make proper decisions about risk and remediation. Obviously, as soon as you go into someone's property to investigate indoor air quality, and then that's a huge issue for residents, and one that shouldn't be taken lightly and should be taken with sufficient reason. So what I'm going to do really is take everyone kind of back to basics so the whole uncertainty vapor intrusion and the actual risk assessment itself really revolves around the conceptual model. And so I'll be going kind of back to basics to the conceptual model, and then talking a little bit about actually indoor air quality itself. Now, whilst many of us won't actually get to the point of actually looking at indoor air quality, the whole purpose of vapor intrusion conceptualization and risk assessment is to predict what that indoor air quality might be. And I think it's really useful to look at the uncertainty within that indoor air quality as a way of kind of tying together all of the kind of composite uncertainty and just kind of make people kind of aware that once you try and predict something in indoor air, that there's a huge amount of uncertainty even when you're measuring it, let alone when you're trying to predict it. And so what is vapor intrusion? Actually, I'm just going to remove my thumbnail. There you go. So what is vapor intrusion? So it's in its basic form, looking at this conceptual model, then it's the movement of VOCs from the subsurface into indoor environments where people living there are exposed through inhalation exposure. And it's a typical source pathway receptor type of relationship, and it's relevant both to planning or future risk or to the Part 2A or current risk scenarios. So in particular, under Part 2A, there might be an impact on or a potential impact on indoor air quality, where you're actually potentially looking at all of the soil pathway of SEPTA, including possibly looking into the building, whereas under planning you might be considering a future building, and there's all sorts of additional uncertainties in that as to how anything additional that you do at a later point in time, such as building a building on land, how that might affect your understanding of the vapor intrusion conceptual model. So really then, and through all parts of that, there are potentially large amounts of uncertainty. So the VOCs that we're talking about are always a combination of being volatile and toxic, and we're familiar with petroleum hydrocarbons such as BTEX compounds and chlorinated hydrocarbons such as trichloroethylene and vinyl chloride. In terms of SVOCs, naphthalene, the most volatile of the PAHs, definitely has the potential to pose vapor intrusion risks under the correct scenario, whereas more highly volatile but lower volatile but more highly toxic BAPs such as benzopyrene don't pose vapor intrusion risks, but they can pose additional risks, typically through dust inhalation exposure. And methane, I mean, methane is a highly volatile hydrocarbon. It's gaseous in its normal state, relatively low toxicity, but as we know, can cause acute risk at high concentration. And really, methane is no different from any of those other compounds. It's just an organic compound with a toxicity, a volatility, and various types of source. And they're not so different to radon either, although it's not an organic compound. Radon is a gas, it's toxic, it gets into buildings, and it's not so different to petroleum hydrocarbons. So radon has a half-life, which reduces its concentration as it migrates through the subsurface and into buildings. And petroleum hydrocarbons are the same. They biodegrade in the subsurface, and as they migrate into buildings, and yet, as practitioners, we tend to separate all these things out, whereas they're all the same. They're just compounds that migrate under fluid flow situations into buildings, and it's a bit of an artificial divide we have between these things. So there are significant health, social, financial, and reputational implications of making incorrect decisions with regards to vapor intrusion risk assessment. And many VI decisions are based on either false positive or false negative interpretations of data, resulting in either unnecessary indoor air quality testing or remediation. And this is, as we'll see, this is particularly common for petroleum hydrocarbons. Or your investigation, you may indicate a false negative conclusion, and thereby and the building occupants thereby having continued inhalation exposure to these chemicals, and that's fairly common with chlorinated compounds, and we'll see why there's a difference there between the two. But clearly, minimizing uncertainty is good to decision making, but minimizing uncertainty needs to be concentrated in where it has the biggest effect for the less money and the less intrusion to people. And really key to minimizing uncertainty is development of a robust vapor intrusion conceptual site model. So back to basics. So VOC partitioning, and this is key to some of the uncertainty. There are three typical VOC phases: absorbed, soil, pore water, or in the soil vapor or gas phase within the pore space. And under certain conditions, when these situations are saturated or exceed saturation in any of those phases, gives rise to a non-aqueous phase, either light, such as petroleum hydrocarbons, or dense NAPL, such as chlorinated hydrocarbons. And the different partitioning between these phases is predicted using theoretical partition coefficients, which are by definition based on equilibrium situations, such as KOC, the soil absorption coefficient, or the Henry's coefficient, which is the air-water partition. And the thing to understand is that VOC partitioning is a highly complex mobile situation, particularly where you have mixtures of different compounds. You might have NAPL, and whereby you get direct vaporization from the NAPL into the unsaturated zone. So it's quite a complex situation. And the important thing for us to remember is that when you predict a soil vapor concentration based on soil or groundwater, it's generally what you predict is far more than you measure. So soil to soil vapor, so that would be 0.1 to 0.001 times under or overestimation. With LNAPL, you might either kind of underestimate it by 50 times to overestimating by 1.4 times. And key to this, and this is also really evident in when we look at methane within boreholes, the actual process of observing partitioning will often change it. You know, we drill boreholes into the ground, we introduce oxygen, etc., and then we measure, and we need to understand how we can actually affect that process. So why do VOCs migrate upwards from the soil up into buildings, which is what we're interested in with regards to vapor intrusion? And really, it's got to do with gradients and flux. So just as your cold beer warms up on a hot day and water flows downhill, things move in the subsurface down gradients. And it's important to understand the idea of flux, which is concentration flow over time, rather than just looking at individual concentrations, either in groundwater, soil, and soil vapor, because it's the flux. So just as in ground gas risk assessment, it's the flux that really makes a difference, and flux within the ground, just as in with ground gas, unless you're dealing with a landfill, the flux under diffusive flow is really slow, and the movement is down a concentration gradient. So you can have diffusion from groundwater through the semi-unsaturated zone into the unsaturated zone, and as we'll see shortly, this is actually a really slow process, diffusion from water into the air phase. And once it's in the unsaturated zone, it can migrate in any direction down a concentration gradient. And it's only really when you get to about a meter or so beneath the building that you start to get increased flux under a vective flow. And the vective flow is flow down a pressure gradient. And in order to have a flow through a building, you need to have a slab with holes in it. So without holes, so if you had a membrane that was fully sealed, you might have a pressure gradient between the two, but you would have no advective flow. You still have diffusion. You can still get diffusion through a membrane, although it's a much slower process than through advection. And the sort of pressures we're looking at, 5 pascals difference. So if you have a lower indoor pressure relative to the subsurface of 5 or so pascals, that's sufficient to drive the advection of soil vapor into the property. And the negative indoor air properties are caused by a number of processes, one of which is the stack effect, which is a delta temperature, delta pressure effect, where warm air moves out of openings, such as chimneys. It can be caused by wind, so higher pressure on the windward versus the leeward side causes a change in pressure within the body, within the building. It can also be caused by building depressurization, particularly in modern buildings where you have mechanical ventilation. If that's set wrongly and you get a net negative pressure relative to the subsurface, then you can draw contaminants into the from the subsurface into your property. Conversely, and you can have, if you pressurize your building, then you effectively turn off vapor intrusion. You push air from the building into the subsurface. And this can complicate investigation, because if you have an indoor source of VOC, you can actually push those into the subsurface where you can measure them, and you might come up with potentially incorrect conclusions about vapor intrusion. Conventional CSM, and I'll go through this really quickly. So we tend to look at VOCs either in groundwater, in soil, or in soil, and we may measure or predict concentrations in the soil vapor phase. And these diffuse and then advect through the floor where they dilute in indoor air. And this dilution through building ventilation is a key mitigating factor. So the flux of contaminants out of the building due to ventilation is generally much higher than the flux through the floor. Where you have preferential openings in the floor, then the balance of that flux gets affected, and you can actually significantly affect indoor air quality. It's also important to consider the presence of NAPL either on the surface of groundwater or in soil unsaturated zone, and also the residual NAPL within the capillary fringe, which we don't measure in boreholes. So by definition, residual NAPL is non-mobile, but in theory at least compose just a significant soil vapor concentration as NAPL, albeit on a much shorter timescale. And we also have the additional complications of considering outdoor sources of VOC, and in particular indoor sources of VOC. A lot of the things we look for in the subsurface are also quite ubiquitous in indoor air. So a typical multiple lines of evidence approach to vapor intrusion then. And this is a typical line of evidence whereby you look in the ground, and the next subsequent phase of investigation is dictated by those results, and you effectively move closer and closer to the point of exposure, which is the actual indoor of the property. Now, this is undertaken unless there's a potential acute or short-term risk, and this is actually really important. So if you have a site, so I'm working on at the moment, it's a chlorinated solvent, potential risk to residential properties. And if you think that there is a potential acute risk or short-term risk, then you should really you should be open to the idea of actually looking into those properties either initially or very quickly as part of your multiple lines of evidence approach. And this is something that is particularly undertaken in the US, where they have far more litigation. And if you have a chlorinated solvent site, then it's very difficult to show that there isn't a risk without actually going into that property and proving that's the case. So it's to rule out the likelihood of false negative assessment. So we typically look in soil and groundwater then, and we compare that with soil assessment criteria or groundwater assessment criteria that we may calculate or that's published. And then in order to reduce conservatism, if those results are saying, oh, you've got a potential vapor intrusion risk, and we know that there is a high level of over prediction when you predict what might be in the soil vapor phase, you actually go and measure the soil vapor phase to take out that uncertainty, and yet then you actually measure what's in the soil vapor phase, which is further along the vapor intrusion route. And you may compare those with vapor GAC that you may calculate, or if you wait for SoBRA to calculate them for you. And thirdly, you might look at subslabs. You're getting closer to the point of exposure, and you want to know what's directly beneath the house, either by taking near slab samples just on the outside of the house, where you may decide, just as Mel was describing, you may drill through the floor and look in the subsurface. And then when you take all of these things into account, you may actually go, well, okay, the evidence points to a potential significant risk, and then you actually go into the indoor environment and measure air quality and compare that with health criteria values. And you need to be really careful about your kind of data quality objectives. And again, as Mel was saying, you need to make sure that the laboratory detection limits, particularly for highly toxic compounds, are sufficiently low enough for you to be able to compare directly with health criteria values. So throughout this process, then we're decreasing vapor intrusion assessment conservatism, but this obviously comes with increasing cost, complexity, and indeed disruption. So where is there uncertainty in all of those, as we'll see in a little bit. So we've looked at a conventional vapor intrusion pathway, so diffusion through the deeper soil from groundwater or from soil, and then advection and diffusion through the floor slab, dilution in indoor air, and then inhalation exposure. But it's really important to, and that's what models, so Johnson-Etcher model would be based on that type of scenario. But what models don't include are unconventional pathways, so preferential pathways. And these may be deep sewers, so migrating actually through the sewer pipe or through the sewer annulus or through any unsealed service entry going through the floor slab, so increasing the advective flow. And fractured bedrock is also, whilst it may not provide an entry into the building, it can provide preferential flow from deeper sources right to the underside of a building. And really importantly, direct contact of in particular LNAPL with building fabric. So you can have really significant vapor intrusion risks. So it's slightly different to vapor intrusion. It's saturation of building fabric and entry into a building through classical vapor intrusion methods or processes, but you can end up with heating oil causing huge indoor air quality issues. When I've been involved with a few where buildings are considered for demolition and people having their health tested and being taken out of their houses. So if you do not consider unconventional vapor intrusion pathways, then you can significantly underestimate vapor intrusion risk. But it's not all bad news. So there are a number of mitigating factors. First of all, biodegradation. So if you have petroleum hydrocarbons, and these can biodegrade very rapidly in the subsurface, and this process is responsible for reducing the vapor intrusion risk from petroleum hydrocarbons to quite low levels, except under certain circumstances, and we'll look into that a little bit further. And biodegradation is also the primary reason for different approaches to petroleum hydrocarbons and chlorinated solvents. In the US in particular, there's a real divergence in approach to looking at petroleum hydrocarbons and chlorinated hydrocarbons. Although in this country, it's less is kind of, it's not understood, but it's I think we're a bit behind on our VOC guidance, the last one being produced in 2009. You can also have freshwater lenses, or if you have, say, chlorinated solvent at depth migrating under property with freshwater above, the rate of diffusive flux through water is really slow. So the diffusion through air is 0.01 centimeters squared per second versus through water, lots of zeros, 1 centimeter squared per second. So it's far slower. So diffusion from a dissolved phase source into air is actually really slow. Okay. And also when we talk about water, due to the much lower diffusion coefficient through water than air, then soil moisture content is also really important. So if you have soils with a high moisture content, then the diffusive flux through that soil is going to be far slower, and that's really important to understand, although we rarely measure soil moisture content in soils. We might look at, we understand whether there's a fine grained layer. So if you had a clay layer, particularly if a clay layer has a high soil moisture content, which it often does, then these can provide quite a strong mitigating factor for vapor intrusion, although you really need to understand, the lateral consistency of that layer to see whether it provides a suitable mitigation measure. And impermeable building foundations, that speaks for itself. So there's no advective flux, but you still have much slower diffusive flux. And positive indoor air pressure, as I mentioned before, if you have a positive indoor air pressure relative to the subsurface, that effectively turns off vapor intrusion and is often used as a method for remediation. And you can also have building subsurface depressurization, which pretty much gives rise to the same thing. So biodegradation, then a quick look at a concentration versus depth in soil graph here. So on the y-axis, we have a decreasing depth from the land surface down to a soil impacted zone, and on the x-axis, increasing concentration. So if you, the process here is flux of petroleum hydrocarbons moving up to the surface, and a key here is the flux of ambient oxygen from the atmosphere through the soil down into the ground. And if you look at the red line, which is the concentration of petroleum hydrocarbons with depth, they're high at depth and reducing through the reaction zone down to potentially zero at the XY axis intersection. And the important thing to note here is the concentration of oxygen is the opposite, so high in shallow soil, low in deeper soils. And that's occurring because of biodegradation. And it's important to measure oxygen concentrations and hydrocarbon concentrations to understand what's going on here. So as we've said, the rates of biodegradation are significant for petroleum hydrocarbons where sufficient oxygen is present. So if you have free phase and the rate of diffusive flux of hydrocarbons into the subsurface exceeds the flux of oxygen, then you end up with anaerobic conditions, and your rate of biodegradation can be quite low, and therefore you end up with a higher vapor intrusion risk. And these rates are much lower for chlorinated hydrocarbons, and this is the key reason, really, as well as the toxicity and dense nature of chlorinated hydrocarbons in water. The lack of biodegradation is the key reason why there's a much different risk profile for these two types of compounds. And chlorinated hydrocarbons can really cause vapor intrusion risk, and there are many examples where indoor air quality has been significantly affected. Even for low concentrations, 10 micrograms per liter of TCE in groundwater can pose a significant vapor intrusion risk and impact on residents. So the real consequences of undertaking vapor intrusion risk assessment and of remediation based on soil and groundwater data alone. So if you're not measuring the actual soil vapor concentrations, you could be vastly overestimating risk, particularly for petroleum hydrocarbons, and you really need to consider the differences between petroleum and chlorinated solvents. And this is shown graphically here. I'll move through this fairly quickly. So with on the left, we have petroleum hydrocarbons, which has a much smaller dissolve phase and vapor plume phase zone because of biodegradation, relative to chlorinated solvents, which have much longer plume lengths and much larger vapor plumes within the unsaturated zone. So that quite clearly shows different risk profiles for those types of compounds. I'm going to go through that. So really then temporal variability in indoor air. So I mentioned if you ever get to the point, so all of our process of undertaking risk assessment is either predicting what's in indoor air, or under certain circumstances, we actually go and measure what's in indoor air. And there's huge amounts of temporal variability in indoor air quality. Just by way of an example, this is real data, subsurface source of TCE measured in indoor air, and each of those blue dots is a sorbent tube sample, sampled consecutively or reasonably consecutively over a 90-day period. So if you take that as being the real data in effect, and you are going and sampling over that 90-day period, and you decide to sample there, you might take a SUMA type canister or a sorbent tube at that point. Or if you take 3 consecutive samples over 3 consecutive weeks during that period, how does that compare with a sample there? Or if you take a 30-day time-weighted average concentration sample there on a sorbent tube, compared to there, you get vastly different results. Or if you, instead of sampling in the spring months, you sample in the winter months, that's hugely different data. So vapor intrusion is generally far more significant in winter months, often due to decreases in indoor air pressure relative to the subsurface caused by stack effect, and we also have less ventilation because people don't open windows. But this is real data, so if you sample that in the spring, particularly at any of those 4 points, and you made a conclusion about people's exposure to contaminants in indoor air, not taking into account their potential exposure over winter, then you may be vastly underestimating risk. Okay, I'll whip through that. That's kind of an Americanism about measuring reasonable maximum exposure and how you can use other kind of scientific processes to try and identify when those RME events, those reasonable maximum exposure events occur. But that's a different talk. And we also, importantly, we also have to try and differentiate between indoor versus subsurface sources, and there are some interesting ways in which you can potentially do that, although we don't really have time to discuss that. So there's one way of really minimizing uncertainty looking at indoor air quality itself, and that's by taking high resolution continuous data. Now this is a US device, which is effectively a portable lab. It's a mobile GCMS, ultra low detection levels for chlorinated and non-chlorinated hydrocarbons, produces results really quickly, and you can look at data in real time, and you can also discretely sample potential vapor intrusion points, measure barometric pressure, indoor differential pressure, wind speed, etc. So you get a lot of data which you can make useful correlations with. But what is really important with this is it's also expensive. It's the patterns in data. So just as we look at ground gas risk assessment and we kind of understand what causes highs and lows in methane concentrations below the ground and in houses, it's the kind of correlation with other events that's key. And this is an example of TCE subsurface source. This is real data. Within a building, they knew they had a TCE problem. They didn't really know where. So they used this portable GCMS, and they were collecting, this is obviously looking back when they looked at their data. So the concentrations were fairly low and the room was closed. Everyone went home at 5 o'clock, the room was closed, the concentrations rose up to a maximum overnight. Someone came in the morning, opened the door, the concentrations immediately dropped down due to dilution. And then when they close the door again, the concentrations go up. So in taking real-time data, you can really start to evaluate what's actually happening. Whereas if you just measured a single time-weighted average concentration over that same time period, it wouldn't tell you very much at all. It would just tell you an average concentration, and you wouldn't really be able to evaluate really what's going on there. This is also another example. This is perchloroethylene in a shop floor subsurface, and they measured concentration over 24 hours, and during the day it was fairly low, and then they kind of observed these kind of increasing spikes up to a maximum overnight, and then it dropped down in the morning. So it's a potentially interesting pattern which you would not see if you took that time-weighted average sample, which is that red dot. So these particular investigators decided to measure over a 14-day period, and they see that it's a repeating pattern. So it's a diurnal pattern with concentrations increasing at night, going down in the day, and being repeated consecutively. This led them to realize that it's actually the HVAC system. So that the ventilation system was, during the day, it had a higher indoor pressure, which was effectively turning off vapor intrusion and lowering TC concentrations in indoor air. And then during the night, because no one was there, the HVAC was automatically stepped down, the differential pressure decreased, and effectively turned on vapor intrusion, and the concentrations go up overnight. And again, looking at this pattern, if you took a 14-day time-weighted average, you would conclude that the exposure is significant and there would be a significant issue. Whereas if you actually look at the concentrations during the day, where there actually is exposure, then they are acceptable. And understanding the pattern would actually lead you to keeping your HVAC system on overnight at a suitable level to effectively turn off vapor intrusion. So the key here really is that there's huge amounts of uncertainty in indoor air quality, but there are methods whereby you can really understand that. But it is it's an in-depth process which requires a fairly high degree of knowledge and kind of financial input. Right, so that's the end of the talk. But I just wanted to finish on a final thought about risk, and this is something that I kind of dwell on a lot. So I'm, as a lot of us, we are contaminated land risk assessors. We're kind of dealing with looking at acceptable risk between 1 in 10,000 to maybe 1 in a million if you live in the States. And what this is an excess risk of dying over a lifetime. And this could be for an individual. And the thing I kind of stew over quite a bit is how do we really try and square that with kind of risks that we all face from climate crisis, which we're potentially talking about existential risk within our lifetime, or even if it's not existential, the risks of billions of people dying. And it's kind of really, as risk assessors, how do we kind of square that, which is actually quite difficult. But as a contaminated land risk assessor, you can do some things. And first of all, this is really understanding uncertainty, and don't overestimate risk. Don't use a lack of knowledge about vapor intrusion to just say, right, we're going to put in we don't really understand it, therefore we're going to put in a vapor intrusion membrane, stick a plastic sheet under the ground, which is an unstable risk mitigation strategy if there's no risk. So the take-home message from me, really, whether it's vapor intrusion risk assessment or ground gas risk assessment, is really understand risk, understand uncertainty, and don't underestimate risk, because that's probably that's done far more frequently than people actually underestimating risk. And secondly, on a slightly lighter note, request more online conference and training events. That's it. Thank you.
Thank you, John. That was really interesting. Just moving on quite quickly due to timing, we'll only have time for one question if anyone wants to get in there first. There we go. Nicole's came through first. So Nicole says, could you ever expect to see the opening of new intrusion pathways for existing buildings due to, for example, new nearby developments interrupting and changing the flux of pollutants?
I guess potentially if that involved inclusion of new deep sewers, or affecting the ground surface can affect how air, oxygen gets into the subsurface, which can reduce biodegradation if you cover the ground surface. But I don't really think that nearby developments would necessarily change the kind of risk profile, unless they were pumping groundwater, which may change the flow of contaminants, or potentially if they are, and these are real situations where you may have air flush drilling, which can push volatile contaminants or gases through fractured bedrock and into houses, and that's a well-known example which resulted in an explosion. But I think more for an individual property is actually looking at creating those preferential pathways, or putting in mechanical building ventilation. And there are real examples where people have done that. They've set it up wrong, and due to creating a negative indoor air pressure, they've actually sucked radon into their property at quite dangerous levels. So yeah, it can occur. Yeah.
Thank you. There is another question from Lauren, but perhaps you could send that reply to that in the chat box or something, so we can move on to Laurence's talk.
Okay.
Good afternoon, everyone. My name's Laurence. I'm going to just try and work out how to share my screen. There we go. Right. I'm going to give a case study this afternoon talking about a real project, long-term air quality monitoring and land remediation project. That really sort of seems to fit nicely with this this group being across IAQM and contaminated land discussion.
Sorry to interrupt, Laurence. You're currently on presenter view. So if you just go to display settings at the top.
Oh, yep.
And then swap presenter view and slideshow. That should work. Yeah, perfect. Yeah, that looks great. Thank you.
Lovely, thank you. So I'm going to structure this talk with a quick introduction into the Avenue Coking Works, its land contamination and the remediation project, and then talk more specifically about my area of expertise, which is the air quality monitoring program that was involved during that remediation work, and talk a little bit as well about community engagement. I think this was touched upon by Melanie in her topic, talking about obviously having to engage with a concerned resident in her case with respect to a mystery odor and some health effects, and in this case, as is the case for air quality in general, I would say it's not something that people can perceive, but it's certainly a health risk and something that people are concerned about. So wherever you have kind of known emissions to air, it's always helpful to be involved in that community, and so that they can understand it and ideally not fear it where there's no need to. So I'll start with the coking works themselves. There's a couple of old pictures here, and more throughout the presentation, but it was an old a coking works where they produced coke for the steel making industry primarily. The site's located in Chesterfield in Derbyshire, and it was operated between 1956 and 1992, and following its decommissioning, due to the fact that during the coking process itself, there's a whole series of kind of byproducts produced that led to the land contamination, such as sulfuric acid, ammonium sulfate, benzene, toluene, xylene, other acids and organic compounds. And in the main, the strategy for the byproducts was just to store them on the site. There was some very large scale kind of open lagoons that material was left in, and the site as a whole, which is upwards of 100 hectares into total site area, was left very contaminated. Following its closure in 1992 and some initial kind of investigations, it was dubbed the most polluted site in Western Europe. I can't vouch for the accuracy of that, but that's certainly something that was bandied around. The total area of land that required remediation was around 98 hectares. And following closure, there was a sort of 20-year program that started with demolition and decommissioning of the coking works itself, and a huge program of ground investigation, which led into site remediation works, sort of beginning in the late 90s and running right through to completion only a couple of years ago. In total, 2.5 million cubic meters of earth were moved, 400,000 tons of material was treated in a thermal desorption unit, and 74,000 cubes of material bioremediated. The whole scheme was kind of was run by Coal Board, or flag, sort of part of Coal Board project with Homes England, with the plan to restore the site and develop it for housing and community parkland. Here's a couple of photos from the site during remediation works. A picture of the thermal treatment plant, which was there for many years and working hard cleaning up a lot of the material. The process following all the site investigation was that material was essentially the whole site pretty much was excavated to some quite significant depth, and all of that material was treated in some way or was stockpiled depending on how contaminated it was, and a large volume of the material was treated with thermal desorption. And the photo on the right is an excavated tar lagoon. So this is one of the big lagoons where there was a lot of byproducts from the coking process that had been stored in there and was an incredibly contaminated part of the site. There was at least 2 or 3 of those on the site itself. In terms of process as a whole, I'll come back to it, but there's here's a pile of material excavated from the tar lagoon being stored prior to treatment. There's a misting spray on that. There was a lot of mitigation put in place during the process to try and basically minimize the emissions to air. In that respect, the key concern was obviously through significant rapid disturbance of all of this material with the contaminants in it, that the pollutants would become airborne and may affect the local community. And the photo on the right here is finished part of this new parkland area, which isn't too far from the big dirty lagoon in the photo I showed on the previous slide. So here's just a quick brief of what the plan was to end up with. If it's clear enough, there's a large area of community parkland, and then the rest of the site pretty much will be developed out into housing as a mixture of dwelling houses and apartments, and this is all sort of well within the under construction phase. It may be the case that actually some of the early dwellings are now occupied on the site. So the air quality monitoring regime that went on during this process, which was started a few years after the sort of work was conceptualized and the site investigation has begun. This was in the early 2000s. Initially, there were 9 permanent air quality monitoring stations set up on locations around the boundary of the coking works and on locations off-site as well. All of these sites were set up to measure various pollutants, particulate matter, such as PM10 and PM2.5, deposited dust, which was then often analysed for species such as silica, carbon content, heavy metals. There was nitrogen dioxide monitoring, PAHs, phenols such as benzene, toluene, xylene, and cyanide, among others. For those familiar with kind of air quality monitoring techniques, there was a sort of range of techniques used. The photo on the right shows in the background big green cabin that had some of the automatic monitoring equipment in it, particularly for particulate, which was continuously analysed, and then various passive analyzers that were located on the roofs of the monitoring sites, including, for example, for the phenols, the monitoring technique was desorption tubes that we often call 10x tubes that Melanie discussed in her talk earlier as well. On top of this, the continuous monitoring regime started initially with baseline gathering. So during all of this site investigation work for the remediation, any remediation work really kicked off, it was all about monitoring to understand what was the baseline, what were the concentrations of these pollutants, what was the pattern of these pollutants through variably through time, so that we could understand it and fully identify any changes or any peaks that might affect, that might be related to the remediation works once they got started. within that, there was also additional often passive monitoring that was undertaken during certain phases of the work. That might be monitoring in close proximity to the tar lagoon during some material excavation or similar, just to understand whether there was measurable emissions coming from those sources. And owing to the nature of some of these compounds being relatively odorous at even quite low concentrations, there was also quite a large regime of odor monitoring that was undertaken during the works, which involved consultant sort of sniff testing around the site during periods, and as well a community survey, which we'll talk about a bit later. The monitoring was ongoing throughout all of these works, and largely at the time there was considerable concern about this, as lessons were already being learned from a similar remediation project at the Corby Steelworks, which some people may have heard about, and at that site there was some quite significant legal cases where they'd sort of linked local birth defects and things to airborne pollution caused by the remediation works at the steelworks site. So the key thing about this whole project was very much doing everything as environmentally consciously, cleanly and safely as possible. For those of you familiar with a bit of air quality monitoring in the IAQM side of things, and doing a bit of this in your role, this is the sort of the ongoing program was pretty much a full-time job. Daily checks were undertaken on the monitoring equipment to check everything was working okay. There was no loss of samples, theft or vandalism. There was fortnightly sample and filter changeovers and monitor span and zero checks, and further monthly full calibrations and data ratification. The odor assessment side of things was a bit more periodic. It tended to be targeted on known activities that might release odors, and being targeted in terms of getting downwind particularly to experience that. Every month there was a public monitoring report that was sent out to the community and published online. And there was continual monitoring of anomalies and trends, and collaboration between the contractors on site and consultants. So this was really there's a sort of partnership between the contaminated land side and the air quality side to identify ways in which activities could be improved to prevent emissions, and constantly communicating whether there were any issues or areas of concern. And the whole works was subject to a quite comprehensive and live, as you'd call it, air quality management plan that was updated throughout the remediation works. Finally, a little bit on community engagement, because this was something that was sort of very key from the very start of the project. You can see from this diagram sort of shows, or this image rather shows the sort of fully completed site as it was maybe back in 16 or 17. There'll be a bit further progressed and more probably some housing have popped up on it by now, but these houses in the bottom have always been there. So there was sensitive communities either side of the site in relatively close proximity. So the teams have been sort of engaging from day one back in 1999 really with the local community to ensure that really, particularly from the air quality side, people understood what was going on, why it was happening, and felt reassured, if anything else, that through the monitoring and things that the kind of Corby Steelworks case study wasn't going to reoccur. There were regular community updates and events, Q&A sessions, things like that went on that people could come along to. Kept the community engaged, responded to their sort of queries and suggestions. In citing the air quality monitoring sites, a lot of key locations that were kind of important to the community were used. So there was a couple of at sort of nearby farms quite close to the site, but then there was primary school, nursery, community centre that were all considered by the local community to be of particular concern. And then, as I mentioned earlier, the monthly summary reports were shared with the community, and there was always these opportunities through the Q&A sessions to field questions about what the air quality monitoring results meant. And finally, we involved the community in odour surveys, and actually enlisted a lot of volunteers as what we'd call odour diarists, where we trained them in being able to undertake a simple odour survey, and they would take kind of routine measurements, record what they had or hadn't smelled, and report back to us. So we had this huge network of the community who would be able to notify us if there had been any odours that had occurred during a period, but also through their involvement felt engaged, and that they, their comments on it were being noted and responded to, rather than having a situation where the community perhaps weren't engaged in that way and were just feeling like they might complain because they could smell tar-like odours, but they didn't know whether that was falling on deaf ears or not. And I think that's my last slide. I'd be happy to field any questions. As I've explained, I'm an air quality expert rather than a contaminated land expert, but I will do my best with whatever you'd like to ask me.
Thank you, Laurence. So if anyone has any questions, please write them in the chat or put your hand up.
When you wait for the questions, I might ask you questions, Laurence. Laurence, during this whole work, did you work at all with contaminated land, like officers or consultancy, or was that this project was handled only from by your consultancy, the air quality consultancy?
Yeah, so I should say this is quite fitting to this this particular group, because this was my involvement in it was very much at the during my early career, so to speak, about 10 years or more ago, and at that time, so I was working for a company called Bureau Veritas. At that time, they were running all the air quality monitoring around the site, but there was a consortium led by Jacobs Babty, as it was at the time, who essentially were running the whole site investigation leading into the remediation side of things. And they were essentially, there were dozens probably of contaminated land experts on site every day. So it was kind of, we were reporting to them essentially, and it was very much a contaminated land led project, and the air quality monitoring was used as sort of information that was provided to them on a regular basis.
Thank you.
Thank you, Anna.
Any more questions from anyone? Otherwise, I'll hand back to Ethne.
Amazing, thank you, Emily. I'll see if any questions come in whilst I'm just doing the closing bit. But a massive thank you to Mel, John, and Laurence for your excellent presentations. It was really interesting to hear the different perspectives and the different types of of work involved within Vapour intrusion and related projects. So thank you very much for taking the time to give those presentations. Also a massive thank you to SoBRA and to Honor and Emily for being involved in this event. I really hope it's been useful to kind of have a chance to look at some interdisciplinary work here. We'd be interested in doing some future events like this. So I will be sending out a kind of feedback form after this. Please do fill that out so that we can make sure that our events are as tailored to what you want as possible. As I mentioned, these presentations have been recorded and will be made available on our YouTube channel and our website. So massive thank you to everyone. I hope you all have a lovely rest of your afternoon. Thank you very much.